Hello, I'm Tyler Kibler, and I'm joined today by Nicolas Null and Elizabeth Lowe. We've received help these past few months from Dr. Sanish Rai of West Virginia University Institute of Technology. Today, we will be talking about testing machine learning models for differentiating between RFI and astronomical data. Pulsars are dense, highly magnetized stars that emit electromagnetic radiation from their poles. This radiation is very concentrated and can only be detected when directed toward the Earth. However, the high rotational velocities of these stars results in their total rotation being measured in milliseconds. They are observed using radio astronomy, necessitating the use of radio telescopes, which are susceptible to radio frequency interference, or RFI. The HTRU dataset is a collection of many of the currently known pulsars, but also primarily made up of RFI, which due to the varying emission patterns of pulsars can be easily confused for a pulsar. The dataset itself contains over 16,000 examples of RFI and another 1,600 examples of actual pulsars, organized by their properties into 8 categories focusing on the statistical characteristics of the integrated profile and DM-SNR curve.
The first step to machine learning is gathering the data. The data can be collected by using the database or from real-time data. Most real-world data is unorganized and will contain missing value, duplicate, and errors. The data must be cleaned up before running through the model. That means the duplicate and missing value must be removed. The data must be randomized, and there shouldn't be any data imbalances. After the data and cleanup is prepared, it can now be split into 2 different datasets. The data will be split into a training dataset and an evaluation dataset. When choosing a model, there are different algorithms that are more suitable for certain datasets. Some are more suited for predicting the relationship between values, while others are better for determining the pressure of the data. Factors such as the content of the data and the site will determine what algorithm will be used. After analyzing the data, the most suitable model will be picked and used for training the data. After selecting the best suited algorithm, the training dataset will run through the model. The model will learn what feature of the data belong to what category and will use the information to improve its ability to classify the data. Once the model is trained, the evaluation set will run through the model, and the result from the test will be a good indicator of how it will perform in the real world. After looking at the result from the evaluation set, the hyperparameter can be tuned to increase the accuracy of the model. The final step of machine learning is prediction. This is where the decision of if the model is ready for practical application is made. After this step, the model will be fed with input data to provide a predicted output.
So applying those steps of machine learning to our own data, we're going to be step 1, preparing our data, when we're going to be splitting into both training and testing sets. And we are also going to have to split into input and output columns. Our second step is going to be selecting models. We selected 5 different models, and of those 5, our best 2, we performed hyperparameter tuning to try and make our models even more accurate. After that, we choose the best model from the hyperparameter tuning and choose that to predict on our unseen data. So on our training and testing split, we have our 2 different sets of data, one that we're going to train on, one that we're going to test on. It's so important that we do that so we're not basing our model's accuracy based on data that it's already seen. And as you can see in these 2 pie charts, both of them, both our training and our testing distribution are the same. So we can say that the RFI and pulsar distribution is the same, and we can accurately say that our testing set accuracy is a good representation of what our overall model accuracy is. So looking at our 5 different performance models, we chose logistic regression, neural network, decision trees, SVC, and k-means clustering. The best 2 models, which were very close, were coming in at around 97% accuracy, and those were logistic regression and neural network. We'll be choosing those 2 to hyperparameter tune. We're performing hyperparameter tuning using sklearn's method grid search. And in this first set, I worked on parameters that had dealing with the neural network. I tried 108 different combinations, and the best model can be seen in our plot. We plotted this, the mean accuracy versus the time. As you can see, there's no correlation between the time that it takes for the model to be created and the accuracy of the model. So we'll just be choosing the highest accuracy model. Our best one was 98%, and our lowest accuracy score was 90%. I used the parameters from Grid Search 1 to move on to Grid Search 2, in which I focused mainly on the hidden layers of the nodes. I tried 75 different hidden layer combinations, and I improved our highest accuracy by a little bit to 98.03, but our lowest was a little bit better than our previous lowest at 95.1. Our last grid search was having to do with the logistic regression. There are less parameters, so there are less points to look at, and they're also more tightly grouped. And you also notice that they took way less time to run. This is because logistic regression is a graphing method where neural network is actually building a large neural network. But here you can see that the highest accuracy was slightly lower than the highest accuracy of the neural network. This means that we'll be choosing the neural network for our final model.
Since we've chosen to work with neural networks, we'll be covering some of the basic concepts. They work by taking inputs in what are called input nodes, such as the 8 attributes of the radio signals used to identify pulsars from the HTRU dataset, and feed them through an algorithm to find the most likely output. The algorithm is created through training. The algorithm primarily is the hidden layer, which is a cluster of nodes, each layer connected by edges that are weighted to determine how the nodes will be applied to the decision. By analyzing the data and the results, a training program is able to create a working algorithm that takes an input and produces an expected output. These outputs are not perfectly accurate, so we measure them based on their success rate, tracking not only how often the algorithm is correct, but also where it is correct, as assigning every pulsar's RFI would still allow it to be 90% accurate, but not actually find any pulsars.
Now that we've looked under the hood on how neural networks work, let's look at how the best parameters perform on this data set. As you can see, it performed at 97.6% accuracy. That's not enough to tell us exactly how it performed. So if you look to the right at our confusion matrix, this will tell us exactly what was predicted and what the actual class was. So if you look along the x-axis, we have what our model predicted, and if you look on the y-axis is the actual class. For example, if you look at the top left, that has the block of data in which RFI was predicted and RFI was the actual class. Where if you look in the top right corner, the predicted class was Pulsar. So our model put out Pulsar, but it was actually RFI in our data set. So this shows us that what exactly our models predicted correctly and the exact number of how many they predicted incorrectly and for each class. And that's summarized also with percentages in the F1 score, which everything to do with RFI was 98% accurate in this model, and everything to do with pulsars was 86% accurate in our model.
The task of separating RFI from pulsar data is very tedious and time-consuming. The goal of the project was to create a machine learning model that can do that automatically. So that way, scientists can track the raw data that they receive and move forward with their research quicker. By collecting astronomical data and running it through our machine learning algorithm, we were able to create a model that had an accuracy rate of 98%. With the model being around 98% accurate, we hope it can be used for practical application in the future. In the future, we will also like to look into parallelizing in our machine learning algorithm to improve efficiency of time and accuracy. We would like to look into using TensorFlow, which could allow it to create a model with better parameters.
The current slide shows the contact information for those who helped with the research as well as our advisor. The following Python libraries were used in our code. We used pandas for importing data sets and preparing data. We used scikit-learn for our machine learning models and parameter tuning. And for data visualization, we used matplotlib and Seaborn. We would like to acknowledge the first two network and Exceed for supporting us in our research. We would also like to thank the University of California, Irvine, who compiled the HTRU dataset and made it open source so that we could use it in our machine learning research project. Thank you for watching and have a good day.